It's important to recognize that when we measure a quantity, the number that we get is never exactly right. For example, if we say that a child is 8 pounds, what does that mean? Does that mean the same thing as saying a child is 8 pounds 0 ounces? Does that mean the same thing as a child as being 8 pounds 1 ounces? So it's important for us to remember that numbers represent approximate values. So for example, if we are in a medical situation and a person is told that something is 4 kilograms, all we can assume is that it was rounded to 4 kilograms. So something rounded to 4 kilograms could have any value from 3.5 kilograms to 4.5 kilograms. Whereas if we're told that something is 4.0 kilograms, that means something different. Now mathematically 4 and 4.0 are the same, but in science 4.0 means something was rounded to 4.0, in which case that would have to be anything from 3.95 kilograms to 4.05 kilograms. So we want to think about what all these things mean. So let's analyze this. We have a measurement. We have an absolute error. We have a lower limit. We have an upper limit. So in our last example, we had 4.0 kilograms. Now our absolute error here, we see it could go from 3.95 to 4.05. So the absolute error then is 0.05. That's the difference between the measurement and the highest value in terms of how we could round it. So our lower value there is 3.95 kilograms. And our upper limit is 4.05 kilograms. Now with this we wanted to find something called the relative error. And the relative error will be the absolute error divided by measurement times 100%. So in our last example, our absolute error was 0.05 kilograms divided by our measurement, which was 4 kilograms. We want to multiply that by 100%. So what will our relative error be? Well, we get 0.0125 times 100%, multiply it by 100, leave the percent in. That's going to give me 1.25%. So the relative error there is 1.25%. So it depends on what your accuracy level is. It depends on how far out you go to round. So for our next example, let's say we're in a medical situation and we are measuring something that is 3.92 grams. So you've got to think about what that could have been. What are the numbers that would have been rounded to 3.92 grams? Well, it would be anything from 3.915 grams to 3.925 grams. So our absolute error will be what? The absolute error is the difference. Again, this is our measurement. This is what we're claiming it to be. So we're putting something on a scale, on a balance, and our best guess for this is 3.92 grams, and we put in the second decimal place. That tells us that that's where we're rounding. So we're looking at the third decimal place and rounding it, or our equipment is telling us the best we can do with the equipment is to hundredths. So that would be 3.92 grams. But the absolute error will be 3.925 minus 3.92. of course will give us 0.005 grams. So if we go through our usual thing, we have our measurement, 3.92 grams. Our absolute error is 0.005 grams. So our lower limit, as we have before, our lower limit is 3.915 grams, and our upper limit is 3.925 grams. So let's look at our relative error in this case. Relative error is absolute error divided by measurement times 100%. So what do we get here? The absolute error, we said, is 0.005 divided by our measurement, 3.92 grams, times 100%. What does that give us? 0.005 divided by 3.92 is 0.00127, and then we have to even approximate this. 0.00128 when you round, times 100%. So you can see that's just 0.128% when we multiply 0.00128 by 100. Let's do one more of these, please. Let's take a look at 27.13 meters. So if that's the case, what is our absolute error, lower limit, upper limit, relative error? So looking at this, we have to think what would get rounded to 27.13, and that would be anything from 27.125 you would round up to 27.13 to 27.135. Anything a little bit below that would get rounded to 27.13. So our absolute error here is 27.135 minus 27.13, or 0.005. So you'll notice we'll always have fives in our absolute error term. We have our lower limit, we have our upper limit already. So again, we can clarify that if you'd like. Measurement 27.13 meters. Lower limit 27.125 meters. Upper limit 27.135 meters. Our absolute error, 0.005. Now from there we want to go ahead and construct a relative error. So that is absolute error divided by the measurement times 100%. Will that give us our absolute error? 0.005 divided by our measurement, 27.13 times 100%. 0.005 divided by 27.13, very, very small number. In fact, it's given to me in scientific notation on my calculator. It's giving me 1.84 times 10 to the negative 4 times 100%. So if we convert that to a decimal, that would be 0.00184 times 100%. So you'll see that's also going to be a very small number, or 0.0184. percent.